All right, kids, we're starting Unit 3. Unit 3 has 3 sections in it. This is Section 3.1 on discontinuity and domain. But what makes this different than what we did in the last unit is that we're not just looking at the graphs, now we're just looking at equations. So it's an algebraic approach to discontinuities and domains. How do you figure them out when you're looking at an equation rather than looking at a graph? And so I've got some margin notes here. This is all the video notes that you had. There's 3 different types of discontinuities. You have a removable hole. You have vertical asymptotes. They're infinite non-removable discontinuities, or jump non-removable discontinuities. Or the other thing that the function could have is no discontinuities. Sometimes there's none and it's continuous. They say on its domain. In other words, wherever the graph exists, it's continuous. And so there were some examples he gave over here. But then the question comes up, where does the function exist? So how can you figure that out? And so that's what domain is where the function actually exists. He did not mention in the video that factoring is hugely important, but I want you to, I have it highlighted and exclamation pointed, because factoring really is the first move you're going to make on these things. And there's 2 situations when you're figuring out discontinuities and figuring out actually for domain as well. You want to take the denominator and set it equal to 0 and solve it. You can't have a 0 denominator. If you have a 0 denominator, that's considered an indeterminate form. And so it's an undefined fraction. I think you probably learned that along the way with your math stuff. So you're going to set the denominator equal to 0 and solve it. And then if you have factors that cancel, that's a hole. If you have factors that don't cancel in your denominator, that's a vertical asymptote. And that's all the stuff about discontinuities. So he went through several examples. Here's the first one. You don't have to factor this one because it's already factored for you. There's nothing really to factor. So you take the denominator. Doesn't matter what the numerator is. It's the denominator that determines where you've got discontinuities or problems with the domain. So x plus 1 equals 0 means that x equals a negative 1. So you have a vertical asymptote. See how nothing canceled? You have no cancellation. That's a vertical asymptote, is at x equals negative 1. Or number 2, this one's already factored for you, but you see how you have a common grouping on the top and the bottom that you can cancel. That's where holes come from. So you have a hole at that factored grouping that you cancel out. X plus 3 equals 0, x equals negative 3. There's a hole at negative 3. But then you still are left with this square root that's in the bottom, and that can't equal 0. Again, you can't have a 0 denominator. So take whatever that is, set it equal to 0. You don't like square roots, so you square both sides. Gives you x minus 2 equals 0 or x equals 2. That's a vertical asymptote because it didn't cancel out. Or the third situation is, check this guy out. If I take, again, I don't care what the numerator is, but the denominator is a 4. 4 can't equal 0. There's no way. So it's continuous. There's no issues. It doesn't have any 0 denominators. So it's continuous on its domain. For wherever it exists, it's continuous. This one now involves some factoring, number 4. So if I'm looking at number 4 and I'm thinking of factoring, I have the top is x plus 1, that doesn't factor, but the bottom I can take an x out, gives me x squared plus 5x plus 6, which then factors into this. Now, you would think and hope that after all that work of factoring, something cancels, and it doesn't in this case. So all you're going to do is take each of these, so you have no cancellations, they're all going to be your vertical asymptotes. X equals 0, x equals negative 3, x equals negative 2, vertical asymptotes. Next one involves AC method factoring, back from algebra. So if I factor the bottom, I get a 2x plus 1 and an x minus 7. The 2x plus 1's cancel. I have a cancel situation. That's a hole. So the hole happens when 2x plus 1 equals 0, or x equals a negative 1/2. Or where x minus 7 equals 0, that's going to be what you're left with. Doesn't cancel, so that's a vertical asymptote at x equals 7. And then number 6, the last one like this. Looking at the denominator is 3. 3 doesn't equal 0. It's going to be continuous for its domain. So that is number 6. So then the question comes up, all right, he does all this stuff with discontinuities, find and classify the discontinuity, but then he changes the whole topic to domains. They're kind of similar, but you'll see that there's some differences between them. So when you're talking domain, here's my side notes. Here's my margin notes for this. You have a numerator and a denominator, n and d, numerator and denominator. Denominator can't equal 0. Well, that's the same idea as what you were doing up top. For the domain is actually going to be all real numbers except where you have a vertical asymptote or a hole. So domain is going to be all real numbers, but it can't be where there's a vertical asymptote or a hole. The other thing that comes up with these domain questions is if you have an even root, like a square root. Square roots always have to stay positive, because if they go negative, then you're in imaginary territory and they don't exist. So, in the real number system. So I've got to, if I have an even root, I have to always keep it greater than or equal to 0. That means it's positive. And the domain's going to be whatever that inequality comes out to be. Now there's a rule for solving inequalities that's going to come up that we need to remember, and that's when you multiply or divide by a negative number, you have to change the direction of the arrow. So keep that kind of in your wheelhouse as we're doing some of these problems. I'll bring it up again as we do examples, but you need to kind of keep that thought in mind from when you learned this back in algebra. All right, so the approach is going to be the same. You want the denominator set equal to 0. You get x equals -1. Well, that's what it can't be. It can't be -1, because if it were -1, I'd have a 0 denominator. So remember, these are asking you for domains, not for what the discontinuities are. So it's all real numbers, but x can't be -1, just like it says right here. All real numbers, but x can't be where you have that vertical asymptote in this case. Number 8, factor out a t on the bottom. Again, nothing cancels. So you've got, these are the values it can't be. If I have t of 0, if I have a t of -3, if I have a t of -2, it can't be those. Those are going to cause 0 denominators. All real numbers, but x can't be them. This one's got a 2 in the bottom. There's nothing that is an issue. So this one is just all real numbers, no problems. This one has a root. Now we're bringing roots into these last few. If I take that, whatever's inside the root, it has to stay positive. Well, in math language, that's greater than or equal to 0. So solve it out. 7x equals -3. X is greater than or equal to a -3/7. That is your domain. The domain is the inequality that you come up with. But sometimes they get a little more complicated. This one, not only can this not equal 0, but it also has to stay positive. I've got two situations for this guy. So the square root of 5 minus x has to equal 0. If I solve that, I get x equals 5. That's what it can't be. If I take this inequality, here's one of those where I'm dividing by a negative. Swing the 5 to the other side. Then I've got to change the direction of the arrow because I'm dividing by a -1. X is less than or equal to 5. Now, you have to put it together. So if x can't be 5, and it has to be less than or equal to 5, then it's just going to be less than when you put it all together, because it's not allowed to be equal to. And so that's your final domain for this one, is x is just less than 5. All right, number 12, last one like this on from the video. You've got your denominator can't equal 0, so it can't be -5, it can't be +5. And your root has to stay positive. So 2x is greater than or equal to 6, x is greater than or equal to 3. Put it all together. It's going to start at 3 and go to the right. So think of a number line. Is -5 even part of that? And the answer is no, because -5 is way off to the left, and it's starting at 3 and going to the right. But 5 is part of it. It starts at 3 and goes to the right. It's going to swing by 5, so you have to say that it can't equal 5. You don't have to say this because this isn't even part of it, because remember it starts at 3. But if it starts at 3 and goes to the right, it's going to swing by this +5, and you need to say it can't equal that. So that was that part of the video. And then the last little bit of the video was talking about putting the two things together. So here are my thoughts from this one. You're going to find the domain first. So if I look at the domain, I can't have a 0 denominator. T can't equal 0. T minus 5 can't equal 0. And what's inside T minus 5 has to stay positive. All right, so T can't equal 0, it can't equal 5, and it has to stay greater than or equal to 5. Putting it all together, again, this is one of those where it starts at 5 and goes to the right. It's not going to touch 0, so you can ignore that. That's out of there for domain. It is not equal to 5, so change your inequality to just be greater than and not equal to, and that's your domain. There are discontinuities here, though. The discontinuities come when t equals 0 and t equals 5. Actually, that's not true. There are discontinuities within this, but because t equals 0 is not part of the domain, you don't need to include that. So it's not in the domain. This one, t equals 5, is not in the domain. It's not equal to. So that means that there are no discontinuities for this within the graph, because the graph starts at 5 and goes to the right. If it equaled 0 or 5, they wouldn't be part of that graph. And so there are no discontinuities for this one. It's continuous on its domain. Last one he's talked about was this guy. Take the denominator, set it equal to 0, take the square root, make sure it's positive. You end up getting an a that's 4. And you've got an inequality where a starts at 0 and keeps going to the right. It's going to hit 4, so that needs to be part of our domain. So a is greater than or equal to 0, but a can't be 4. And we have this discontinuity at a equals 4 because that gives you a vertical asymptote. So in summary, he said, finding discontinuities was how he started it. He doesn't talk about the importance of factoring, but I did. You want to set the denominator equal to 0 and solve it. If the factor cancels, it's a whole. If the factor stays, it's a vertical asymptote. And that's in the denominator you're concerned about. Doesn't matter what the numerator is. And then for finding domain, the denominator can't be 0, and you have to keep even roots positive. And that's how you're finding domain. All right, so let's try a few problems together. Let me grab mine. We're going to start with number 6 is the first one on my list. All right, number 6, let me show you. So again, here, let's check the directions. Find and classify each discontinuity. So he's only asking about where the discontinuities are. He's not asking us about domain. All right, discontinuities. Set the denominator, well, first of all, factor, right? Set the denominators equal to 0. I'm going to factor first. Now this one only has 2 terms. There's no middle term to this, so that makes me think of difference of 2 perfect squares. Is 9 a perfect square? Is 16 a perfect square? And you say, yep, they are. So here's how it's going to factor. Here's my function. I have a 3x plus 4 on top. I have a 3x plus 4 and a 3x minus 4, difference of 2 perfect squares. Square root of 9 is 3. Square root of 9x squared is 3x. Square root of 16 is 4. Different signs in the middle. And you can see you're set up now where you've got a common group on the top and a common group on the bottom. Bang, bang, they're out of there. They cancel. That creates a hole wherever that is. So I know I have a hole when 3x plus 4 equals 0. Solve it out. 3x equals negative 4. X equals negative 4/3. There's my hole. But I'm still left with this guy here that's on the bottom. So if he's on the bottom, he can't cancel out. He's a vertical asymptote, and that happens when 3x minus 4 equals 0. 3x equals 4, x is 4/3. And there you go. Did you find the discontinuities and classify them? Yes, you did. Okay, number 6. Next one is number 7. All right, so number 7, this one again, you want to start with factoring thoughts. And so...
For an interruption, just a reminder to please wipe down your desk and area before leaving class. Once again, a reminder to please wipe down your desk and area before leaving class. Thank you.
All right, here we go. Factoring out a t. That leaves me with 3t plus 1. Don't forget that one placeholder. When you distribute this back, you have to make sure you get to here. If you just do 3t, it's not going to work. The bottom, I'm factoring out a t. Leaves me t squared plus 3t minus 28. Then I'm thinking of the factors for 28 that add up to negative 28 that add up to be 3. So that's a plus 7 and a minus 4. Here I go. T plus 7, t minus 4. And I'm looking, here's my numerator factored. Here's my denominator factored. And the only thing they have in common is the t that's out in front. So Mr. T goes bye-bye. He creates a hole. There's a hole when t factored out, equals 0. But I'm still left with a t plus 7 and a t minus 4 that don't cancel. And again, I don't care about the numerator, I'm just looking at the denominator. So that means that I have vertical asymptotes when t plus 7 equals 0 or t minus 4 equals 0. And you'll notice that I use a little curly QT because otherwise they look like plus signs to me. All right, there's my discontinuities. Whole at 0, vertical asymptotes at negative 7 and 4. Then I go to number 9. Number 9 is next on my list. If I take the denominator and set it equal to 0, here's what happens. X squared equals a negative 4. Well, I don't want x squared, I want x. And so I'm going to have to square rooty. Here comes square rooty. That means that x equals plus or minus the square root of a negative 4, which is imaginary. It's not in my real number system, which means that this guy has no discontinuities. He is continuous on its domain. Wherever he exists, he is continuous. All right, next step. Changes directions. Identify the domain this time and use inequality notation. So that's a part of keeping it positive. So I've got two situations for number 12. The first situation is the denominator can't equal 0. So the square root of 36 minus 6x can't equal 0. I want to know when it equals 0 because that's when it can't equal 0 is going to cause that. So I square both sides, square rooty. Square both sides. 36 minus 6x is 0. I solve it out. Swing the 6x to the other side. Divide by 6. Gives me 6. But the second part is that square root has to stay positive. So 36 minus 6x has to be greater than or equal to 0. And what I'm going to do is I'm going to solve that. So swing the 36 to the other side. Negative 6x is greater than or equal to 0. Oh, x greater than or equal to negative 36. I brought him over. Divide by a negative 6. Here's the flare should be going off in your head. When you multiply or divide by a negative number, you got to switch the arrow. Here it goes. Divide by negative 6. X is less than or equal to negative 36 divided by a negative 6 is 6. Now remember, domain. It can't equal 6, that's going to cause a 0 denominator. But it has to start at 6 and go to the left. Put it all together. X has to be not equal to 6, but it has to be less than 6. And that's your domain for that one. All right, next is 13. 13 says, I should think factoring, right? My denominator there is x squared minus 2x minus 15. I need two numbers that multiply to negative 15 and add to negative 2. I would think that should be x minus 5 and x plus 3. Well, that didn't do me much good for the top, right? There is no x plus 7, so I've got no holes. Nothing is canceling out. But I do have two parts here that I'm going to set equal to 0 because I have vertical asymptotes, technically. I know the question's asking you for domain. But you want x minus 5 equals 0, so x equals 5. And x plus 3 equals 0 is x equals negative 3. Remember the domain. Domain's going to be all real numbers, but it can't equal those two values of negative 3 or 5. They're vertical asymptotes. Can't have that. 16. This one's a cube root. Now cube roots, if you knew how the graph went with cube roots, they're kind of sideways squiggles like that. They can equal anything. It's an odd root. This is an odd root. Our rules come for even roots are the ones that have problems. So this is an odd root, which means its domain is all real numbers. It has no issues. No problemos. All right, we've got 2 to go. Changing up directions again. This one says identify the domain and classify the discontinuities. I'm going to think factoring when I look at number 23. Again, there's no middle term. So this one is going to have a difference of two perfect squares situation. The square root of 64 is 8. The square root of 25 is 5. Kind of gives you a hint from the numerator. Here Here's how it factors. I have the 8x minus 5 up top. I have an 8x minus 5 and an 8x plus 5 on the bottom. My 8x minus 5's cancel. What happens with that? That creates a hole, right? So I've got a hole. My hole happens when 8x minus 5 equals 0. Solve it out. 8x equals 5. X is 5/8. But I still have another group in the denominator that's going to create a vertical asymptote. Now the vertical asymptote for this guy is going to be, when that equals 0, 8x plus 5 equals 0. Solve it out. 8x equals negative 5. X is negative 5/8. And so the two things that my function can't be are positive or negative 5/8. And the question was asking me domain. I'm kind of out of room. I'm going to put it over here in box 24. My domain is all real numbers, but x can't equal plus or minus 5/8. All right. So did we do it? We identified the domain. Yep. Did we classify the discontinuities? Yep. Hole and vertical asymptote. We're good to go. All right. Last one. 26. Here we go. This one, there's nothing to factor. No factoring going on. I'm looking at this though, and I know that x minus 8, my denominator, can't equal 0. So I'm going to solve that. X equals 8. When x equals 8, I have a 0 denominator. Can't have that. All right. But I also need to keep my square root here positive. So I need this guy to be 5 minus x has to stay positive, greater than or equal to 0. And I'm going to solve that. So I'm going to have the 5 on the other side, negative x comes over here, it got negative 5. Flare's going off, I'm dividing by negative. So I'm going to have to change the arrow. So it's x is less than or equal to 5. All right, let's put the domain together. Domain. If I start at 5 and I go to the left, do I care about 8? He's not even part of the graph. So my domain is only this part here. X is less than or equal to 5. Again, because if I start at 5 and go to the left, 8 isn't part of that. 8 is to the right. So 8 isn't even part of my graph. Which means 8 causes an issue with the discontinuity, right? But 8 isn't even part of the graph. So guess what? This one is continuous. There are no discontinuities. So it's asking us to classify discontinuities. We're going to say discontinuities. There are none. Because there is one at 8, but 8 isn't part of the graph. Which is why he suggested that you find the domain first. All right, you are not doing the skills review or any of those things. Your task is to go back and complete numbers 1 through 27. All right. Shoot me an email if you have any questions, and I will see you soon.